We're also going to take a quick look at what kind of instructions you may see in a modern architecture, and this will just be a brief overview. We will not study any specific instruction set in detail in this course. So far we have discussed the operand model and concluded that register-based model is a pretty good choice for modern computers. Now we're going to discuss instruction formats and what kind of instruction mix you may have, conditional codes, addressing modes, and what kind of immediates you may have in your instruction set. Before you even get that far, one overriding question you have to ask is if you would like to design an instruction set with a fixed instruction format or a flexible format. So here at the top we show a picture of the VAX format, which was the variable format. It was pretty much no upper limit how long an instruction could be in the VAX architecture. Once more, it was designed back in the CISC days. Then we have the fixed instruction format, and this is what is very common in modern processors today, where all instructions are represented with the same number of bits in memory, and we have some specific fields that always mean the same thing, or it's maybe just a few variations of what each bit or field what purpose they have. So typically the opcode, the bits that define exactly what's going to be executed, has a fixed place, and we have some address fields. This could be identifying register 1 and register 2 and register 3, for example, or maybe it could identify something else. You also have a variable instruction set representation, what's called hybrid here, where you have a few different instruction lengths. So this is, for example, what's being done in x86, where instructions can be very small or very large depending on how many bits you need to express exactly what the instruction should do. And it's quite natural that if you have a variable instruction format, you can represent a code in a much more compact way, because you only use sort of the number of bits you actually need to represent each instruction. While if you have a fixed format, it has to be one size fits all, so you have to squeeze all the instructions. So it's the longest, most complex instruction that's going to define that format. Here we're going to look at a fixed format representation of an instruction set that's been defined by the authors of this book. And this instruction format always represents an instruction using 32 bits. Always the first 6 bits is an opcode that defines what operations should be performed, but the other fields of an instruction depends on what type of instruction it is, if it's an intermediate type, a register type, or a jump type. So an intermediate type means that you, beyond the opcode, can identify 2 registers, a source destination and a destination register, and also an immediate, sort of a constant that can hold up to 16 bits. The register type contains, well, the opcode, and then you could identify 2 source registers, register 1, register 2, and then a destination register where you put the result. And since this type is used by the ALU instructions, and there are the ALU instructions are in a far majority, there is also a field here with 11 bits that can further specify exactly how you would like to perform your operation. And then you have the jump type, and the jump type beyond the opcode has a one giant immediate, and this immediate is used as an offset, so it's a constant used as an offset to be added to the PC. So that's when you do PC relative jumps. These are the only 3 formats in this architecture. The kind of instructions in this architecture we're going to talk about is quite simple. So it's what's called the load store architecture, where you either do a load or a store. And if you don't do load and store, you do an ALU operation, which is the adds. And you can also have a control instruction. So the load, this is what the mnemonics looks for in the assembler. this says load word, put the result in register 1. So you always work towards the left. You put the result in the leftmost item of these instructions. And what you're going to put in register 1 is identified by register the contents of register 2 plus a constant 30. So the meaning here is put into register 1 the memory location identified by the value stored in register 2 plus the constant 30. So that's the mnemonics we're going to talk about. Stores are the same but the other way. Store word, we're going to put the word into this memory location identified by the contents of R2 plus the constant 30. And it's the value stored in R1 that we're going to store in that location. So here is the meaning. Memory location identified by contents of register 2 plus the constant 30. That's where we're going to put the data, and the value we're going to put there comes from register 1. Then you have normal ALU operation, and ALU operation never ever writes or reads from memory. It only reads and writes from registers in what is called a load, in this kind of load store architecture. So what this may say, put the result in R1, and you get the result by adding the value stored in R2 and the value stored in R3 once more. Here's the meaning of that instruction. And then you have some kind of control instruction. Then when this control instruction here says branch is if equal to 0, R1. So this is this branch if R1 is equal to 0. And the place you're going to branch to is by looking at the current program counter. You add the immediate constant Kalle to that counter plus 4. The program counter is always normally incremented by 4. And in this situation, we also add Kalle as an extra offset to figure out where the computation should continue. So generic ALU instruction. So for integer arithmetic, you encode what type of instruction you have by using a combination of letters. First, you say what the normal arithmetic operation should be, the add, subtract, or whatever things you may add here. And then you encode if it's going to be assigned or unsigned. So you may add a U here if it's unsigned. If it's not, then we assume it is assigned. And then it could be a register or an intermediate form for the ALU operation. And if it's intermediate form, you add an I. So out of these possible combinations you can have here, the ones we most often going to use is just the plain format. So in the dark letter, it's the I and the sub that we'll be interested in. Likewise, you can have logic operations and or SOR, and you can have that they as a register or as an immediate. And what we're going to do in this course is just to use the vanilla versions here. The and the or, not the immediate, or the SOR, but not the immediate versions. There is also a need for you to sometimes build larger constants than you can build if you only have an immediate that's 16 bits large. So there is a special register where you can load the upper half of the register, the 16 upper bits of the register. We're not going to use that in this course either. When you decide how to handle conditional branches, there are 3 different options. So one option, which is maybe a little old-fashioned these days, is to use condition code. So the way that works is that most instructions or operations executed have some kind of side effects on some kind of condition code bits or some condition code flags. And when you perform a branch instruction, you decide whether or not that branch is going to be taken or not, depending on one specific of these bits. So you're sort of looking at side effects from previous instructions when you do the branches. Conditional registers is regarded to be a cleaner way of doing conditional branches these days, where you in the register itself name a specific register, and then the condition code may specify, just as we saw previously here, if that named register is equal to 0, then you can take some kind of actions. Then you have a combined instruction where you do a compare and branch at the same time, where you sort of do a much larger kind of CISC kind of instructions where you can compare several registers with each other, and if they happen to be the same or not the same, and then you take some actions. So what we're going to do use in this course is the conditional registers. So this creates a much simpler control, and that's what the authors Hennessy and Patterson also decided in their design of their ISAs. This is a good idea. So we're going to see an instruction that says branch is equal to 0 or branch is not equal to 0, and we're going to compare to a specific register. And if that holds, then we're going to say that the program counter is going to be the current value of the program counter plus 4 plus some immediate. The immediate can have a value at most of 16, constant of 16 bits. That's what we're going to use in this course. Of course, sometimes you do want to jump further than that. Then we will need to combine this with a kind of jump, which is non-conditional branches, and they have ways of jumping further than that. They have also ways of doing register relative jumps. We're also going to have some special magic ways of handling floating point jumps that depends on floating point registers. Not in this course, we're not going to use that, but that is something that is often included in these kind of instruction sets. Finally, the last thing we're going to look at is sometimes we are going to look at floating point arithmetic as well. So here we have the usual suspects: add, sub, mult, divide, and so on. And they can be doubles or single. So if you add an extra d, that means double. So add d, that means a double precision. So that normally means that you actually, in this kind of architecture we're going to talk about here, which assumes to be a 32-bit architecture, if you have an add double, that means that you're actually going to take the value of a specific register and its neighboring register, 32-bit each, to put together a double, which is 64 bits. So floating point double is normally 64-bit arithmetics. That's it for instructions. So just to repeat again, we have load, and this could say load double. That means we're going to load two registers, or just load word. Here means a single 32-bit value. Load that into a register, and we identify the place we're going to load from memory by the value stored in R2 plus a constant. Store, in this example here, word, doing the same thing backwards. We locate the place where we're going to store the value with by adding 30 to the content, the value stored in R2, and then the value we are going to store in that location is R1. We have an ALU instruction, which is only a register-based instruction. We store the value to the result into the left, and then so this is the destination register to the left. Then we have two source registers, R2 and R3, and the operand is opcode here will decide what kind of operation we're going to do. And then we have the branch, which is a branch with respect to a value of a register. So if the named register in this case happens to be equal to 0, then we're going to add the constant 16-bit constant color to the current PC value, and it's going to go PC. So actually this has an error here. PC, it's the value of PC plus color plus 4. That's what you should get here. Finally, just a few words about the RISC versus CISC. So CISC, the complex set instruction computers, that was something that grew out of the need to come up with instructions that suited assembler programming of human beings. The authors of this book, they introduced, both of them at the same time, independently, a new kind of architecture called RISC, reduced instruction set computer. This is typically what they were teaching was that you should have load store architectures. So either you do load store or some kind of ALU or a branch, but you never have instructions that do all of these at the same time. So you don't have an add instruction that gets one of its values from a register and the other value to be added directly from memory. You have fixed length instruction formats because that simplifies the design. You have very few addressing modes. So I showed you the predominant addressing mode we're going to use here, constant added to a register value to identify a place in memory. You have general purpose registers. This is in contrast also to CISC, where some registers had some special semantic meanings in some instructions. Here, all the registers are the same, and you explicitly have to name which register you are referring to. The authors of the book also added quite a lot of other various suggestions that we're going to talk about. One is interlocking pipeline stages. MIPS stand for microprocessor without interlocking pipeline stages. We're going to talk about that in a little while. And that was the Stanford contribution. So MIPS comes from Stanford. It comes from John Hennessy, the author of the book. At Berkeley, they had the RISC processor. So they were the ones that came up with the name RISC. That's Patterson, David Patterson. They came up with, beyond all these other things here that's listed that's common to both products, they came up with something called register window that we will discuss. And they also came up with a scheme called delayed branches that at first may look like a good idea, but these days is pretty much banned from modern computer designs.